December 31st, 1944. Aboard the destroyer USS Hyman in the North Atlantic, 700 miles west of the Azores, Lieutenant Commander James Russell stood on the bridge wing as dawn broke over a grey sea, watching his gunners track a German reconnaissance aircraft circling at 12,000 feet. The plane stayed well beyond range of the ship's 5-inch guns, observing, reporting their position to U-boat command. Russell had seen this before. The Luftwaffe would spot them, transmit coordinates, and within hours submarines would converge on their position. Standard procedure called for firing time-fused shells set to detonate at the estimated altitude of the target. Russell's gunnery officer had already calculated the settings. 11 seconds of flight time. Detonate at 12,000 feet, but Russell gave a different order. Load proximity, he said quietly. Fire when ready. The forward gun crew loaded shells, marked with red bands, shells that looked identical to standard high-explosive rounds but contained something revolutionary hidden inside their nose cones. The gun fired. The shell arced upward toward the aircraft. At 70 feet from the target, without striking anything, the shell exploded. Shrapnel tore through the reconnaissance plane's fuselage and wing. The aircraft staggered, turned sharply, and fled eastward, trailing smoke. Russell watched it disappear over the horizon. 3 months earlier, that plane would have circled with impunity, calling in submarines, watching men die. Now it ran. The destroyer's crew cheered. But Russell understood something they did not yet grasp. The shell that had just saved their lives represented a technological achievement so significant, so secretly developed, that even most naval officers did not know it existed. A device that could detect a target without touching it, calculate distance in microseconds, and detonate a warhead at the precisely optimal moment to inflict maximum damage. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The proximity fuse, officially designated the variable time fuse but known to those who understood its true nature as the VT fuse, had been in development since 1940. For 4 years, physicists and engineers had worked in secret to solve a problem that had plagued military forces since the invention of artillery. How do you make an explosive shell detonate at exactly the right moment when that moment depends on countless variables you cannot predict or control? The question was not academic. In 1943, American naval forces in the Pacific fired an average of 1,200 anti-aircraft shells to destroy a single Japanese aircraft. 1,200 shells, each weighing over 50 pounds, each costing the equivalent of 2 weeks' pay for an industrial worker, fired into the sky, set to explode at predetermined altitudes based on estimates of target height and speed, hoping that shrapnel would intersect with an aircraft moving at 200 miles per hour. The mathematics were brutal. A shell detonating even 50 feet from a fast-moving aircraft produced almost no effect. Shrapnel dispersed in a sphere. Most of it flew uselessly into empty air. The small portion that travelled toward the target arrived with diminishing velocity and density. To reliably destroy an aircraft required a direct hit or a detonation within 30 feet. Achieving that with a timer set on the ground, fired at a moving target, at varying distances, against an aircraft that might climb, dive, or turn at any moment, was nearly impossible. Gunners compensated by firing more shells. Anti-aircraft batteries consumed ammunition at rates that strained supply lines and manufacturing capacity. Ships carried enormous quantities of shells because naval doctrine assumed that destroying a single attacking aircraft required hundreds of rounds. The waste was staggering. The inefficiency was accepted as unavoidable, until it was not. The problem of the anti-aircraft shell was fundamentally a problem of prediction. Artillery had always required prediction. A gunner firing at a ground target calculated range, wind, temperature, barrel wear, and dozens of other variables to determine where a shell would land. But the target stayed still. Anti-aircraft gunnery multiplied the complexity exponentially. The target moved in 3 dimensions. It could accelerate, decelerate, climb, and turn. The shell flew a ballistic arc that took seconds to complete. During those seconds, an aircraft traveling at 200 miles per hour covered nearly 600 feet. By the time the shell reached the altitude where the aircraft had been, the aircraft was somewhere else entirely. Military forces had developed two solutions to this problem, both inadequate. The first was the contact fuse. The shell had to physically strike the target to detonate. Against aircraft, this was nearly impossible. The shell had to intersect with a moving target measuring perhaps 40 feet in length, flying at high speed, in three-dimensional space. The odds of a direct hit were so low that contact-fused shells were effectively useless against aircraft. The second solution was the time fuse. A mechanical clockwork device inside the shell measured elapsed time from firing. When the preset time expired, the fuse detonated the shell. This allowed shells to explode at specific altitudes, creating a barrage of shrapnel through which aircraft had to fly. Time fuses were better than contact fuses, but still desperately inefficient. The gunner had to estimate the target's altitude accurately, estimate wrong by just 500 feet, and the shell exploded harmlessly above or below the aircraft. The gunner also had to estimate the target's future position, fire at where the aircraft was, and the shell would detonate in empty air. Fire at where the aircraft would be, but guess wrong about its speed or direction, and again the shell was wasted. In 1941, when German aircraft attacked British cities and German submarines hunted Allied convoys, the mathematical reality of anti-aircraft fire was grim. British anti-aircraft batteries fired an average of 20,000 shells to destroy a single German bomber over London. 20,000 shells. The Luftwaffe lost aircraft, but not because of accurate anti-aircraft fire. They lost aircraft because sheer volume of fire occasionally produced a lucky hit. The strategy was attrition through ammunition expenditure. Fire enough shells, and eventually one would detonate close enough to damage an aircraft. It was, as one British gunnery officer noted, like trying to kill a bird by throwing rocks. Throw enough rocks, and you might hit one, but you would run out of rocks long before you ran out of birds. The Japanese attack on Pearl Harbor on December 7, 1941, demonstrated the consequences of ineffective anti-aircraft fire with brutal clarity. American ships anchored in the harbor fired thousands of shells at Japanese aircraft. Few hit. The Japanese lost 29 aircraft out of 350 that attacked. Most losses came from accidents and operational failures, not from accurate anti-aircraft fire. American gunners fired frantically at targets they could see but could not hit. The weapons existed. The ammunition existed. The will to fight existed. What did not exist was a way to make shells explode at the right place at the right time. Military doctrine in 1942 accepted the inefficiency of anti-aircraft fire as an unavoidable reality of modern warfare. Training manuals taught techniques to maximize hit probability, fire in barrages, create overlapping fields of fire, concentrate multiple guns on single targets. These techniques improved results marginally, but the fundamental problem remained. A shell that missed by 50 feet was as useless as a shell that missed by 500 feet, and most shells missed by far more than 50 feet. Naval commanders planned operations around the assumption that anti-aircraft fire would consume vast quantities of ammunition while achieving minimal results. Ammunition ships accompanied every major naval operation, carrying hundreds of thousands of shells. Logistics officers calculated supply requirements based on the expectation that ships would fire hundreds of rounds per engagement. Industrial production prioritized shell manufacturing. Factories ran multiple shifts, producing millions of shells annually. Everyone understood the system was wasteful. No one believed it could be improved significantly. The doctrine extended beyond mere acceptance of inefficiency. It shaped tactical thinking. Naval formations were designed to concentrate anti-aircraft fire, allowing multiple ships to fire at attacking aircraft. The theory was that massed fire would increase the probability that at least some shells would detonate near the target. In practice, This meant that fleets sailed in tight formations that made them vulnerable to submarine attack in order to improve anti-aircraft effectiveness. The trade-off was accepted because no alternative existed. Aircraft carriers were particularly vulnerable. A single bomb or torpedo hit could disable a carrier, removing its aircraft from combat and potentially sinking a ship that represented years of construction time and enormous material investment. Carriers required escort ships specifically to provide anti-aircraft protection. Entire destroyer squadrons existed primarily to fire anti-aircraft shells at Japanese aircraft attacking carrier groups. The destroyers themselves were vulnerable to aircraft attack, but their purpose was to put enough shells in the air that attacking aircraft might be deterred or damaged. The psychological dimension of anti-aircraft fire was almost as important as its physical effects. Gunners who fired continuously at attacking aircraft maintained morale and fighting spirit even when hits were rare. Silence from the guns would have been devastating to crew morale, so ships fired thousands of shells, creating noise, smoke, and visible bursts, demonstrating resistance even when the actual defensive effect was minimal. This was understood and accepted. Anti-aircraft fire was as much about psychology as about physics, but by 1943, the ammunition expenditure was becoming unsustainable. American industrial production was vast, but not unlimited. Every shell fired at an aircraft was steel, explosive, and manufacturing capacity that could not be used elsewhere. The millions of shells fired annually represented resources that could have built tanks, artillery pieces, or additional aircraft. Military planners began searching for ways to improve anti-aircraft effectiveness, not because they believed dramatic improvement was possible, but because the current system consumed resources at an unsustainable rate. They were looking for marginal improvements. What they would receive instead was a revolution in weapons technology that would change warfare fundamentally. But in 1942, that revolution existed only as an unproven concept in a research laboratory where physicists were attempting something that most military officers believed was impossible. The National Defense Research Committee established Section T in September 1940 to investigate the possibility of a radio-based proximity fuse. The name itself was deliberately obscure. Section T operated under contract with the Carnegie Institution in Washington, led by Dr. Merle Tuve, a physicist who had spent the 1930s studying the ionosphere using radio pulses. Tuve understood that radio waves could be transmitted, reflected, and received in microseconds. He believed this principle could be applied to detecting targets and detonating explosives. The theoretical concept was straightforward. Place a miniature radio transmitter and receiver inside an artillery shell. The transmitter would emit radio waves continuously. When the shell approached a target, the radio waves would reflect off the target's metal surface and return to the receiver. As the shell got closer to the target, the strength of the reflected signal would increase. When the signal reached a predetermined threshold indicating the shell was within lethal range, an electronic circuit would trigger the detonator. The practical challenges were enormous. The device had to fit inside a shell nose cone measuring approximately 3 inches in diameter and 5 inches in length. It had to survive being fired from a gun, experiencing acceleration forces exceeding 20,000 times the force of gravity. The acceleration lasted only a few milliseconds, but during that time every component inside the shell experienced stress that would instantly destroy normal electronic equipment. The vacuum tubes that formed the basis of all radio equipment in 1940 were fragile glass devices designed for stationary use in carefully controlled environments. Subjecting them to 20,000 Gs would shatter them instantly. The device also had to operate reliably after being stored for months in ship magazines, where temperature and humidity fluctuated constantly. It had to function in rain, in freezing temperatures at altitude, in tropical heat. It had to be manufactured by workers with no electronics experience, because the precision required was beyond normal manufacturing tolerances. And it had to cost less than 3 times the price of a conventional shell, or the military would refuse to adopt it regardless of its effectiveness. Tuve assembled a team of physicists and engineers who had never designed military equipment. They were academics, researchers, theoretical scientists. They understood radio propagation and electronic circuits, but they had never built anything intended to withstand the violence of being fired from a gun. The team began by testing whether vacuum tubes could survive gun launch at all. They mounted standard vacuum tubes inside dummy shells and fired them from guns. Every tube shattered. They tried reinforcing the tubes. The tubes still shattered. They tried mounting the tubes on shock-absorbing materials. The tubes shattered. After 3 months of failures, the team concluded that conventional vacuum tubes could not be used. They needed tubes specifically designed to withstand acceleration forces far beyond anything attempted before. Working with manufacturers, they developed vacuum tubes with reinforced glass envelopes, shortened internal elements to reduce vibration, and modified mounting structures. These rugged tubes survived gun launch, but they were larger than the space available inside a shell nose cone. The team had to miniaturize everything. By early 1941, Section T had developed prototype vacuum tubes that fit inside a shell and survived firing. But the complete fuse required not just tubes, but also a transmitter circuit, a receiver circuit, a battery to power the electronics, and a detonator circuit. All of this had to fit in a space smaller than a coffee cup and had to function reliably after experiencing forces that would kill a human being instantly. The battery problem was particularly difficult. The fuse needed power to operate, but only for the few seconds between firing and detonation. A battery that could provide sufficient power for that duration, fit inside the available space, survive gun launch, and remain stable during months of storage did not exist. The team developed a reserve battery that activated only when the shell was fired. The spinning motion of the shell in flight closed electrical contacts that brought the battery online. This solved the storage problem but added another component to an already crowded space. By June 1941, Section T had built complete prototype fuses that functioned in laboratory tests. The fuses could detect metal objects at distances up to 100 feet and trigger detonation circuits reliably. But laboratory testing was far from combat conditions. The fuses needed to be tested by firing them from actual naval guns at actual targets. The Navy agreed to conduct trials, but with deep skepticism. Naval officers had seen many proposed improvements to anti-aircraft fire. None had delivered significant results. They expected the proximity fuse to fail like everything else. The first live-fire tests occurred in August 1941 at the Naval Proving Ground in Dahlgren, Virginia. Section T engineers traveled to Dahlgren with crates of prototype fuses, carefully packed to prevent damage during transport. The Navy provided a 5-inch gun, standard ammunition, and a drone aircraft as target. The test protocol was simple. Fire shells equipped with proximity fuses at the drone. Observe whether the shells detonated near the target. Compare results to time-fuzzed shells fired under identical conditions. The first shell fired failed to detonate at all. The fuse had been damaged during loading. The second shell detonated prematurely, 2,000 feet from the target. The third shell passed the target without detonating. Navy observers took notes with expressions that made their opinions clear. This was another failed experiment. By the 10th shell, engineers were troubleshooting frantically, trying to determine why the fuses were not functioning as they had in laboratory tests. The problem was radio interference. The ship's own radar was overwhelming the weak signal from the fuse receiver. Once the ship's radar was shut down, the fuses began working. On August 12, 1941, a shell equipped with a proximity fuse exploded 60 feet from the drone target, destroying it completely. The Navy observers requested another test. The second shell exploded 70 feet from a new target, destroying it. A third test. The shell exploded and destroyed the target. The Navy officers asked to see the fuses. They examined the devices, noting the complex electronics packed into the small space. One officer asked how many shells would be required to destroy a target using proximity fuses compared to time fuses. The Section T engineers estimated that proximity fuses would reduce the number of shells required by a factor of 10 to 1. Instead of 1,200 shells to destroy one aircraft, perhaps 120 shells would suffice. The Navy officer responded that even if the estimate was accurate, the proximity fuse would not be adopted. It was too complex, it would be too expensive, it would require training that sailors could not master, it would fail in combat conditions. The entire concept was impractical. Fuze and his team returned to Washington, understanding that technical success was insufficient. They needed to demonstrate that the fuse could be manufactured in large quantities, that it could be used by ordinary sailors without special training, and that it would function reliably in actual combat. Section T established the Applied Physics Laboratory at Johns Hopkins University in Silver Spring, Maryland, to develop manufacturing processes. The laboratory hired engineers with production experience and began designing assembly lines specifically for proximity fuse production. Every component had to be standardized. Every manufacturing step had to be documented. Quality control procedures had to ensure that fuses would function after months in storage. By December 1941, when Japan attacked Pearl Harbor, the Applied Physics Laboratory had designed production processes but had not yet manufactured fuses in quantity. The attack on Pearl Harbor changed everything. The demonstrated ineffectiveness of American anti-aircraft fire convinced Navy leadership that new solutions were essential. Proximity fuzzes went from being an interesting experiment to a critical priority. The Navy ordered 100,000 fuzzes for testing and evaluation. Section T had 6 months to develop manufacturing processes that could produce fuses in quantity while maintaining quality standards. The challenge was unprecedented. Electronics manufacturing in 1942 was a craft industry. Skilled technicians hand-assembled radio equipment 1 unit at a time. Proximity fuses required mass production by workers with no electronics experience, producing thousands of units daily to tolerances measured in thousandths of an inch. The Applied Physics Laboratory designed assembly lines where each worker performed one simple task repeatedly: insert a component, solder a connection, test continuity, pass the assembly to the next worker. The process resembled automobile manufacturing more than electronics manufacturing. Workers needed no understanding of how the fuse functioned. They needed only to follow procedures exactly. Quality control inspectors checked every 10th fuse, then every 100th, ensuring that manufacturing consistency remained high. By June 1942, the production line was manufacturing 500 fuses daily. By December, production reached 5,000 fuses daily. But manufacturing was only half the challenge. The fuses had to be tested in combat. The Navy selected the Pacific Theater for initial deployment, far from Europe where captured fuses might be examined by German scientists. In January 1943, the first combat shipment of proximity fuses arrived at naval bases in the Solomon Islands. Ships received the fuses with detailed but simple instructions. Load them like any other shell. Fire them at aircraft targets. Do not attempt to adjust or modify them. Report results. The instructions emphasized that the fuses were highly classified. Crews were forbidden to discuss them. If a ship carrying proximity fuses was in danger of capture, the fuses were to be destroyed immediately. January 5, 1943. The cruiser USS Helena engaged Japanese aircraft attacking Guadalcanal. The ship's 5-inch guns had been loaded with proximity-fused shells for this specific purpose. Japanese bombers approached at 10,000 feet, formation tight, expecting the usual pattern of time-fused bursts that rarely achieved hits. Helena's gunnery officer gave the order to commence firing. The forward guns fired. The first shell exploded 75 feet from the lead bomber. Shrapnel tore through the aircraft's wing. It fell burning into the sea. The second shell exploded near another bomber. The aircraft staggered but continued flying. The third shell destroyed a third bomber completely. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Within 3 minutes, Helena had fired 32 shells and destroyed 5 aircraft, damaged 3 more, and scattered the formation. The surviving Japanese bombers turned away without attacking. Helena's crew watched in stunned silence. They had just witnessed something unprecedented. anti-aircraft fire that actually worked, that destroyed targets efficiently. That changed the tactical situation immediately. The gunnery officer sent a message to Pacific Fleet headquarters. Proximity Fuzes extremely effective. Request maximum supply. Other ships that had received proximity Fuzes reported similar results. The destroyer USS Nicholas fired 12 shells at attacking aircraft and destroyed 3, damaged 2. The battleship USS North Carolina fired 40 shells and destroyed 4 aircraft. The pattern was consistent. Proximity Fuzes reduced ammunition expenditure by factors of 10 or more, while increasing effectiveness dramatically. But the most significant test came at Rendova Island on July 29, 1943. Japanese aircraft attacked American positions in waves throughout the day. Ships offshore fired proximity-fuzzed shells continuously. The statistics were remarkable. American ships fired approximately 1,500 rounds and destroyed 17 aircraft, damaged 9 more. The ratio was approximately 100 rounds per aircraft destroyed. Compare this to previous engagements where 1,200 rounds per aircraft was the norm, and the improvement was unmistakable. But the impact went beyond statistics. Japanese pilots reported that American anti-aircraft fire had become far more accurate. They described shells that seemed to explode precisely as they passed near aircraft, as though the shells were seeking them out. The psychological effect was significant. Attacking American ships had always been dangerous, but pilots had accepted calculated risks. Now, the risk seemed far greater. Shells that would have exploded harmlessly above or below targets were now exploding at exactly the right moment. Japanese aircraft began avoiding American ships whenever possible. Admiral William Halsey, commanding South Pacific Forces, sent an assessment to Admiral Ernest King, Chief of Naval Operations, in August 1943. The proximity Fuze, he wrote, had changed naval anti-aircraft defense fundamentally. Ships that had been vulnerable to air attack were now dangerous to approach. The ammunition expenditure had decreased dramatically, while effectiveness had increased proportionally. Halsey recommended immediate deployment of proximity Fuzes throughout the Pacific Fleet and urged that production be increased to maximum capacity. The Navy placed orders for millions of proximity Fuzes, but security concerns remained paramount. German forces could not be allowed to capture intact Fuzes and reverse engineer the technology. Throughout 1943, proximity Fuzes were used only in Pacific naval operations, never over land where dud shells might be recovered. The technology remained classified at the highest levels. Most American military personnel did not know proximity Fuzes existed. This changed in December 1944 during the Battle of the Bulge. German forces launched their final major offensive in the West, attempting to break through Allied lines in Belgium. The attack achieved initial surprise and significant penetration. American forces were pushed back. German artillery fired continuously. Allied positions were threatened. On December 24th, fog lifted sufficiently for Allied artillery to engage German formations. American artillery battalions had been issued proximity Fuzes specifically for this contingency. The Fuzes had been modified for use in artillery shells rather than anti-aircraft shells. Instead of detonating near aircraft, they would detonate above ground targets, showering German forces with shrapnel from above. The effect was devastating. German soldiers had no protection against airbursts. Foxholes and trenches that provided cover from conventional artillery offered no protection from shells exploding overhead. Casualties increased dramatically. German commanders reported that American artillery had become far more lethal. They could not understand why. Shells seemed to be exploding precisely at optimal height to maximize casualties. The psychological impact matched the physical casualties. German soldiers who had survived years of combat reported that the new American artillery was more frightening than anything they had previously experienced. The success of proximity Fuzes in combat during late 1944 forced a fundamental reassessment of weapons production priorities. Before the Battle of the Bulge, proximity Fuzes had been manufactured at a rate of approximately 100,000 per month. After their effectiveness became undeniable, the War Production Board designated proximity fuse manufacturing as a critical priority. Production facilities expanded rapidly. By March 1945, American factories were producing over 1 million proximity fuzzes monthly. The manufacturing infrastructure required was extraordinary. The Applied Physics Laboratory coordinated production across multiple facilities. Western Electric manufactured the vacuum tubes. Eastman Kodak produced the condensers. General Electric built the batteries. Hundreds of smaller contractors manufactured specific components. Assembly occurred at dedicated facilities where workers, mostly women, performed repetitive tasks with precision that would have seemed impossible years earlier. A single proximity fuse contained over 100 components. Each component had to meet exact specifications. A deviation of a few thousandths of an inch could cause failure. Quality control became an obsession. Every fuse underwent multiple tests during assembly. Electrical continuity was checked. Components were X-rayed to verify proper positioning. Completed fuses were tested in centrifuges to simulate gun launch forces. Random samples were fired from actual guns to verify function. The rejection rate never exceeded 3%, a remarkable achievement for such complex devices manufactured at such scale. By war's end, American industry had produced over 22 million proximity fuses. 22 million miniature radio systems, each more complex than most radio receivers of the era, mass-produced by workers who had never seen a radio circuit before. The cost per fuse dropped from approximately $50 in 1943 to approximately $18 by 1945, roughly 3 times the cost of a conventional time fuse. The military accepted this premium because proximity fuzzes reduced ammunition expenditure far more than 3 to 1. A ship that might have fired 300 conventional shells at an attacking aircraft now fired 30 proximity-fused shells and achieved better results. The net savings in ammunition, shipping, storage, and manufacturing capacity were enormous. But the impact extended beyond economics. Proximity fuzzes changed tactical doctrine. Naval formations no longer needed to be designed primarily around concentrated anti-aircraft fire. Ships could operate with greater spacing, reducing vulnerability to submarines and torpedoes. Carriers could conduct operations with fewer escort vessels because each escort was far more effective at anti-aircraft defense. The strategic calculus of naval warfare shifted. Japanese aircraft that had been able to accept calculated risks when attacking American ships now faced dramatically higher casualty rates. Kamikaze attacks, Japan's final desperate tactic, became even more costly because proximity fuzzes detonated near aircraft that might have otherwise crashed into ships even after being hit. In Europe, proximity fuses transformed artillery effectiveness. American and British forces fired artillery barrages using proximity fuses against German positions throughout early 1945. German defensive positions that had been relatively safe from conventional artillery became death traps. Trenches offered no protection. Only deep bunkers provided safety, and bunkers made troops immobile and vulnerable to other weapons. German commanders requested information about the new American shells from intelligence services. German scientists examined fragments recovered from battlefields, attempting to understand the detonation mechanism. They concluded correctly that some form of radio proximity detection was involved, but German industry lacked the manufacturing capacity and resources to develop similar weapons by that stage of the war. The Soviet Union received proximity fuzzes through Lend-Lease but in limited quantities. Stalin's government requested manufacturing specifications and permission to produce proximity fuzzes domestically. The American government refused. Proximity fuse technology remained classified at the highest levels. Even Britain, America's closest ally, received completed fuses but not manufacturing specifications until after the war ended. The United States maintained absolute control over this technology because military leadership understood its significance. Winston Churchill, in his post-war memoirs, called the proximity fuse one of the 3 most significant military developments of the war, alongside radar and the atomic bomb. His assessment was not hyperbole. Proximity fuzzes had changed warfare fundamentally by solving a problem that had seemed unsolvable. They had demonstrated that scientific research could produce weapons that altered tactical and strategic situations decisively, and they had proven that American industrial capacity could manufacture complex technology at scales that enemies could not match or counter. The proximity fuze's success came with costs that statistics alone cannot capture. Every shell that detonated above German positions during the Battle of the Bulge killed or wounded soldiers who were sons, brothers, fathers. The increased lethality of American artillery meant more German casualties, more families destroyed, more lives ended. The cold calculus of military effectiveness measured success in enemy casualties and ammunition efficiency. But each casualty represented a human life ended by a device designed specifically to maximize killing efficiency. German soldiers who survived proximity fuse barrages described the psychological impact in post-war interviews. They reported that conventional artillery, while dangerous, provided some protection through cover and dispersion. Soldiers could take shelter in trenches or foxholes and survive near misses. Proximity fuses eliminated this margin of safety. Shells exploded overhead without warning. Shrapnel rained down from above. There was no effective defense except deep underground bunkers, and those were not always available. The constant threat of airbursts created psychological stress that conventional artillery did not produce. Soldiers became reluctant to leave protected positions, even when tactical situations required movement. American soldiers who witnessed proximity, fuse effectiveness, had different reactions. They understood that the weapon was saving American lives by killing enemy soldiers more efficiently. Artillery forward observers reported that proximity fuses allowed them to suppress enemy positions with fewer rounds, reducing the time American infantry spent under fire. Company commanders noted that German defensive positions could be neutralized more quickly, allowing advances to proceed with fewer casualties. The weapon was doing exactly what it was designed to do: make American forces more effective at destroying enemy forces. But some American soldiers and officers questioned the ethics of weapons designed specifically to maximize casualties. Proximity fuses made war more efficient at killing. They represented the application of scientific knowledge and industrial capacity to the problem of destroying human beings. The moral implications troubled some participants. A weapon that killed more effectively was a weapon that created more widows, more orphans, more grieving families. The fact that those families were enemy families did not eliminate the moral weight. These concerns were rarely expressed publicly during the war. Military necessity took precedence over ethical considerations. The United States was fighting enemies that had started the war, that had committed atrocities, that threatened American interests and values. Developing weapons that could end the war more quickly by killing enemy soldiers more efficiently was not only acceptable but obligatory. Scientists who worked on proximity fuses believed they were contributing to victory and saving American lives. They were correct, but they were also creating weapons that would remain in military arsenals long after World War II ended. The proximity fuse became standard equipment in American and Allied arsenals. The basic principle, using radio waves to detect targets and trigger detonation at optimal distance, remained valid. Later versions became more sophisticated, more reliable, more lethal. Modern proximity fuzzes use radar, laser, or infrared detection. They are smaller, more accurate, and more dependable than the World War II versions. They are used in anti-aircraft missiles, artillery shells, bombs, and rockets. The technology that Section T developed in 1940 has evolved into weapons systems used in conflicts worldwide. The long-term strategic impact of proximity fuses extended beyond their immediate military effectiveness. They demonstrated that scientific research could produce decisive military advantages. This lesson influenced post-war military policy. The United States established permanent research institutions to develop military technology. The Applied Physics Laboratory continued operations after the war, conducting classified research for the Department of Defense. Other research laboratories were established at universities and private facilities. Military funding for scientific research became a permanent feature of American science policy. The proximity fuse also demonstrated the importance of manufacturing capacity. American industry's ability to produce 22 million complex electronic devices during wartime exceeded anything enemy nations could match. This industrial superiority, combined with technological innovation, created military advantages that could not be overcome by tactical skill or strategic planning alone. Post-war military planning emphasized maintaining industrial capacity and technological leadership as essential components of national security. Lieutenant Commander James Russell, who had ordered proximity fuses fired at the German reconnaissance aircraft on December 31, 1944, survived the war. He returned to civilian life, worked as an engineer, and rarely discussed his naval service. In a 1978 interview conducted by a naval historian, Russell was asked about the proximity fuse and its significance. His response captured both the technical achievement and the human reality of the weapon. "The proximity fuse," Russell said, "changed everything about anti-aircraft warfare. Before proximity fuses, shooting down an aircraft was mostly luck. You fired hundreds of shells and hoped one would explode close enough to matter. With proximity fuses, every shell had a realistic chance of destroying the target. It made our ships safer. It made our jobs easier. It saved American lives by killing enemy pilots more efficiently. I understood that then, and I understand it now. But I also understood that we had developed a weapon that killed people with greater efficiency than anything before it. That knowledge has stayed with me." Russell's reflection captured the fundamental tension inherent in military technology. Proximity fuzzes were a triumph of scientific ingenuity and industrial capacity. They solved a seemingly impossible problem through clever application of radio technology, miniaturization, and mass production. They saved American lives by making American weapons more lethal, and they killed thousands of enemy soldiers and pilots who died because American engineers had learned how to make shells explode at precisely the right moment. The story of the proximity fuse is ultimately a story about the application of human intelligence to the problem of destroying other humans more effectively. Section T. Scientists were not cruel people. They were physicists and engineers who believed they were contributing to a just cause. They worked long hours under intense pressure to develop technology that would help win the war. They succeeded brilliantly. The proximity fuse worked exactly as intended. It changed warfare. It demonstrated American technological and industrial superiority, and it killed thousands of people. Dr. Merle Tuve, who led Section T, received numerous awards for his work on the proximity fuse, including the Presidential Medal for Merit. He continued scientific research after the war, making significant contributions to radio astronomy and geophysics. In later interviews, he expressed pride in the proximity fuse's technical achievements, but also acknowledged the moral complexity of weapons development. "Science," he noted, "is neutral. Scientists are not. We chose to apply our knowledge to military purposes because we believed the cause was just. Whether that justification remains valid is a question each person must answer individually." The proximity fuse remained classified until 1946, when sufficient information was released to allow public understanding of the technology without compromising military security. Full technical details remained classified for decades. Even today, certain aspects of modern proximity fuse design remain classified. The basic principle is well known. The specific implementation details that make modern proximity fuses effective are not public knowledge. When Lieutenant Commander Russell stood on the bridge of the USS Hyman on that December morning in 1944 and ordered proximity fuses fired at the German aircraft, he was participating in a moment that represented both human achievement and human tragedy. The shell that exploded 70 feet from the aircraft without striking it demonstrated that American scientists had solved a problem that had frustrated military forces since the invention of anti-aircraft weapons. It demonstrated that American industry could manufacture complex technology at unprecedented scale. It demonstrated that American forces had weapons that enemy forces could not match. And it demonstrated that human ingenuity, when directed toward the problem of killing more efficiently, produces solutions that are technically brilliant and morally troubling. The proximity fuse saved American lives. That is undeniable. It also killed enemy soldiers and pilots more efficiently than previous weapons. That is equally undeniable. Both facts are true simultaneously. The weapon was necessary given the circumstances of World War II. The weapon was also a device designed specifically to maximize casualties. These contradictions cannot be resolved. They can only be acknowledged. 70 years after the proximity fuse entered combat service, the technology remains in use. Modern militaries rely on proximity-fused weapons for air defense, artillery, and missile systems. The basic principle that Section T developed in 1940, detect a target without touching it, calculate distance, detonate at optimal range, remains valid. The implementation has evolved, but the concept endures. The sign that came down in Major General Doolittle's office ordered fighters to bring bombers back alive. The new sign ordered fighters to destroy enemy fighters. That change in doctrine won the air war over Europe. The proximity fuse represented a similar change in doctrine. Instead of accepting that anti-aircraft fire would be inefficient, engineers developed technology that made it efficient. Instead of accepting high ammunition expenditure, they created weapons that achieved results with fewer shells. Instead of accepting limitations, they solved problems. Whether that solution was worth the cost is a question that cannot be answered with statistics or technical specifications. The proximity fuse worked. It accomplished exactly what its designers intended. It changed warfare, and it killed thousands of people more efficiently than previous weapons. All of these statements are true. History remembers the proximity fuse as one of the war's most significant technological achievements. That memory is accurate, but it is incomplete without acknowledging what that achievement meant in human terms. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.